Good evening and welcome to Pattern Pursuit. My name is Mike Houston and I'm the moderator of the webinar. I teach algebra and calculus near Pittsburgh where I use TI technology to make tough to teach, tough to learn concepts accessible to all my students. With us tonight is Karen Camp and John Lemaster. Karen was instructor of math ed at Yale for 15 years and previously taught high school and middle school math in Connecticut and Pennsylvania. She's been a T-Cube national instructor since 1998, providing professional development at conferences, workshops, and webinars. Karen is passionate about using technology effectively to enhance student understanding in mathematics. Karen, we're excited to have you with us.
Glad to be here, Mike.
And John's been a part of the T-Cube family for just a couple of years, longer than Karen, since 1993. He presents annually at conferences, rates math activities, and provides feedback to Texas Instruments on software and products. John's a 2019 T-Cubed Leadership Awardee. He teaches mathematics at Purdue University, Fort Wayne, and his passion is to empower students with technology to mathematize their world. So, John, it's great to have you with us as well.
It's awesome to be here tonight. Thanks.
Karen, will you talk through the agenda for tonight?
Certainly. We have an action-packed pattern pursuit for you tonight. After this welcome and introductions, we are going to investigate patterns numerically, graphically, and algebraically to create models. We will explore patterns that lend support for common algebra rules that we teach using both the TI-84 family and the TI-Nspire. And we're going to experience some unexpected surprises with fractions and figurate numbers. To close out the night, Mike's going to do a webinar drawing at the end for some lucky winner.
Thanks so much, Karen. And John, how about the expected outcomes?
Well, we have three, and the first is modeling. So we're going to see these tools to use, home screen, lists, tables, scatter plots, etc., to be able to empower us to model number patterns. The second is to make connections to those number patterns to algebra and middle school math topics so that they really tie into what we do every day. And the third one is then the technology that connects all of these together to help those connections get built and to have concepts that glue them all together so that they're retained. I have one little suggestion for the rest of the evening. If you are tempted, like I am always tempted, to pull out your technology and try to follow along, resist that temptation, because you'll get the best experience out of this webinar by not using the technology and trying to follow, but looking at the recording later and then following at your own pace. So that's the way you'll get your most enriched experience.
Thanks so much, John. Tonight we'll be using the chat window to send general messages, but if you have any questions for John or Karen, use that Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. All right, Karen, kick things off with some habits of mind.
So I've always had a ton of fun with numerical, visual, and algebraic patterns, geometric patterns as well, can't leave geometry out of it. But one of the things that I've looked at most often in my teaching is the mathematical habits of mind that are ways of approaching problems and thinking about math concepts. These are habits that students can use to more closely emulate what mathematicians might do, and it's something that I aspire to do in my teaching, and I hope that you have time to do this as well. But here's what struck me: out of the 8 general habits of mind that these researchers have put forth, students should be pattern sniffers, but they also should be experimenters, describers, tinkerers, inventors, visualizers, conjecturers, and guessers. And we're going to be doing a little bit of all of that tonight. Okay, what I would like to do is I would like to share my screen, and we're going to dive in to some patterns tonight. And here are the calculators. And what I want to begin with is I want to begin with a little pattern here that I'm going to call triangle trains. And what I'd like you to do, please, is take a look at these four visuals, these four stages of the pattern, and see if you can come up with some description in your mind of how you think this pattern grows, or what you think the next stage might look like. And Mike and John, I cannot see the chat, so hopefully people will put into the chat in about 10 more seconds. I want you to put in what you think is the way this grows, or what you think the next one is. So if everyone would type, and then 5, 4, 3, 2, 1, submit into your chat. And I cannot see the chat, but hopefully John or Mike, can you tell me what they say in the chat?
Yes, we've got some wonderful ideas, adding 2 each time. And then actually, if n is the stage, some formulas suggested as n plus 2.
Perfect.
So 6 triangles pointed up and filling in the gaps.
Okay.
So we've got a lot of traffic and suggestions.
Perfect. Okay, so what I was trying to do, I'm so glad that John gave us a little taste of what you all are sharing in the chat. What is really important about these activities is that, yes, there's an answer to what the 5th stage will look like, but there's not one right answer for how this pattern grows or how you think an equation should be built. And so what I'm going to do is I'm going to take you through some of the tools that I use with my students to build this pattern. And so what my students will do with this pattern is they will write down what they think the next thing in the sequence did, and then they're going to fill in the chart for the number of triangles that they think are in each image. So let's take a look at our TI-84. We will get to the Nspire a little bit tonight as well. Let's put in for stages 1, 2, 3, 4, and 5. Let's put in our number of triangles, and this number of triangles was 3, 5, 7, 9, and I think that you will agree that there is going to be 11 triangles in the 5th one. And in the lab worksheet that I use with this activity with my students, I want students to describe in words how they think the pattern grows, and there's more than one right answer. And like John said, some people saw odd numbers, some people saw that it grows by 2 each time, some people see a bottom of a certain number and then the top slices into it. But if students are trying to build that description, that verbal description of the pattern into an algebraic model, one of the tools they can use to help them is a scatter plot. So on the TI-84, you go to second stat plot and you can turn it on. It's using lists 1 and list 2. You can also turn that on straight from the y = screen if you already know that it's the right lists. And you also should pick a window, and the variety of windows that you can do, but a nice easy thing to do is to do number 9, zoom stat, under the zoom menu, and that will fit a window to your data. I often say to students that what I really like to do is I really like to adapt the zoom stat window so I can see my axes, because I really do like seeing those axes. And I also like to leave room for this to grow. And I hope you all can see that what we've got here is we've got a linear pattern. Even though my window that I've chosen isn't an equalized square grid, I can square it off if I want by doing the zoom square. Okay, that just squares off the grid that I started with. If you don't like any changes you make with zoom, go up to zoom and over to memory and do zoom previous. But in any case, let's talk about the algebra of what we think this is. So somebody might say, well, I think that this pattern starts with 3 and then adds 2 every time, and they're building it like a slope-intercept form. So they might say it starts with 3 and it adds 2 each time, but the second stage is only adding 1, 2. So I'm going to do 2x minus 1. And we can see if that works, if that goes through our data, and it does. Somebody else might have noticed that this is odd numbers. So 2x plus 1, because the first odd number is that we have here is 3. So 2 times the stage number plus 1 will get us those odd numbers. And now when we go back to the graph, I wonder if this is the exact same algebra. And what we can do is we can arrow all the way to the left in my graphing screen, press enter, which allows us to change color, but it also allows us to change graphing style. And if I use this tracer ball style, we can see if that algebra is the exact same, and it is. And those of you who are teaching middle schoolers or Algebra 1 students, you can show equivalence from algebra expressions in this way. And then John said there was somebody who noticed that we had a number at the bottom. Like in this case, we have 2 plus the 1. Then in the second stage, we have 3 plus the 2. And the third stage, we have 4 plus the 3. So that student might say, well, I have 2 plus the 1, and my 2 is x plus 1, because it's a 2 and I'm on the first stage. And then I add the stage number. Just like here, what we can see for 4 is 5 on the bottom plus 4. And let's see if that one covers it, and it indeed does. So those are all the different ways, some of the different ways that we can write equations for this. When we're looking at the lab sheet, after the students have given an equation for the number of triangles in step X, then I ask them to make a prediction. How many triangles will there be in step 41? And each student who's working on this is going to be prompted in step 6 to go back and come up with a different way to do this. Number 7, generalize. How does the growth rate appear in your linear model? And we can find out that growth rate is the slope. And whenever I do lab sheets, I have extensions because sometimes students are working faster than others. So you might decide that you want to do a perimeter instead of just the number of triangles. You can do the perimeter of the triangle train. Now, this same pattern can appear in different ways. I'm sure you've seen other visual patterns that have odd numbers. And I want to just share with you a TI-Nspire activity called Growing Patterns, and this is going to be in your documents that you can download after the webinar. And what this is having us do, it's going to have us click through the stages. I'm actually going to make this a little bit bigger so you can see this nice and large. The TI-Nspire has the ability to give us a split screen. So we have our visual pattern, our scatter plot, and our list all in the same screen. You click through the stages here, and I think you'll see, let me go back actually a second. We have 3 in the first stage, like my triangle trains, 5, 7, 9, and 11. And this activity actually lets students type on that text box. Instead of the question mark, you can type in the algebraic expression that you have here. And so one of our algebraic expressions was y equals 2x plus 1. And we can check it and see it right there in the screen. So for you TI-Nspire users, this is a really nice activity. And this one carries on and has some other patterns that you can do. We're going to go back to triangles, though, because I have another pattern in mind. So my next triangle pattern is, instead of triangle trains, I've got triangle towers. And would you take a moment, and I want you to imagine what the next image in the sequence looks like, and I think that's not too hard to imagine. What I want you to think about here is the total number of small congruent triangles, blue or white, blue and white. We want to count up all of the small triangles here. Okay, so here, whoops, let me go up here. Here we go. Here we have one small triangle. Okay, and the next one I think you'll see is 4 small triangles. And the next one, we have 1, 2, 3, 4, 5, 6 blue ones and 3 white ones. So that's 9. And then the next one over here, we have 1, 2, 3, 4, 5, 6, 7 on the bottom row, then 5, then 3, then 1. So we have 16. Some of the ways I'm counting might be ways that you think that this grows. But if you are taking a look at all of the small triangles, what pattern do you see here? How might you describe this pattern? And do you think that there's going to be 25 in the next one? So somebody could say, I counted up blue plus white. So the 9 would be, sorry, let me go back to the 4. The 4 is 3 blue, 3 plus 1. The 9 is 5 plus 3 plus 1. Actually, I'm sorry. Let's say you're doing layers. I apologize. 5 plus 3 plus 1 in layers. Okay, and then the 16 would be 7 plus 5 plus 3 plus 1, because these could be sums of odd numbers, or you can add them up as blue and white. But these are going to be the odd numbers, and let's pop back to our calculator here. And I'm going to go into my stat edits, and we have 1 triangle, then we have 4, then we have 9, and then we have 16 and 25. Now, this, to us math teachers, this is obviously a pattern of perfect squares. Students may not name it that way initially, and certainly we want to talk about it that way. But when you have these squares, if you're going to go and take a look at the graph that we had at the scatter plot, our scatter plot looks different now. And students should be able to look at the scatter plot and see that this is not a constant growth situation where you add the same number each time. This is not linear. And it is going to be building out a parabola representation on the graph. If we go into our stat lists again, when you have a linear list, you can tell that the difference between the terms is all the same. It has a constant growth factor being added. Here, the growth is not the same at each stage. And what we're going to do is we're going to use a command, and this is both on the 84 and on the Nspire. You want to take this list and you want to find the common difference between the elements of the list. That command is under the list commands here. So second list, it's under ops, and it's this number 7 delta list. And so in L3, I'm going to take the difference between the terms from L2. I want it to subtract successive terms. And now we see that we have a different amount getting added at each stage. And if you go to L4 and you again take that common difference for L3, you'll see that that second set of differences is constant. So in a quadratic growth, you're going to get the second change is going to be constant, the second differences. In linear growth, it's the first set that is constant. So we, of course, can see here that our pattern is going to be x squared, and the graph will match with that model. let's go back to our picture for a second. And what if you look at your triangle towers and you only look at the blue ones, not blue and white? So blue only. And if you look at blue only, we have one blue to start. Whoops. And then we have 3 blues in the second stage. And then we have 3 plus 2 plus 1. We have 6 blues in the third stage. In the fourth stage, we have 4 plus 3 plus 2 plus 1. And in the fifth stage, you can imagine that we're going to have 5 plus 3 plus 2 plus 1. These numbers is another wonderful pattern. These are not the square numbers like we started with. These you may know of as triangle numbers. And John's going to spend some time on this a little bit later. I'm just going to put them into our list 2 to see what happens with that. And we want to check the common differences here. And you'll notice that nothing happened. My common differences in list 3 did not change. That's because once you set a list, once you give it its operation, it is a static operation unless you do something very special. Let me show you this. If I want to take this L3, I have to press enter from the top row, and then I clear that list there. I want to tell it to take the differences of L2, but I don't want to lose it if I have another pattern going in. So I start with a quotation mark, which is alpha plus, and then I grab my list command from the ops, list ops menu, and I want delta list of L2, close parentheses, and close my quotations. And if you noticed, I got this little lock up here. That lock indicates that we have a formula that is now built into this list. I'm going to do the same on L4. I'm going to press enter, clear out the old data, quotations, second list from the ops menu, get the delta list. I want to do that on L3. And the advantage of these locked lists is that now my common differences will continue to compute even if I change the information in my lists. Okay, let's take a quick look here. I am going to clear out the Y1 because I don't know what the formula is. I don't even know whether this pattern, well, I should know if this pattern is linear or quadratic because I can see that my second differences are constant. So this is going to be quadratic. So here's my graph. And so I think it's quadratic, but maybe you're having trouble building that formula. So I just want to put,
Can I just ask you, is this on the Nspire too, the delta list? Is one of the questions in the chat.
On the Nspire, John, I'm so glad you asked that. On the Nspire, if I create a document here, sorry, here we go. If I create a document, when you have a list and spreadsheets, I'm sorry, this has gotten very small, squashed here. When you create a list and spreadsheets, you have to have it, you have to name the lists at the top. Oops. Here we go. Name the list at the top in order to use it. And then you can set a formula right here. So if I have stage 1, 2, 3, 4, 5, and then my triangle numbers were 1, 3, 6, 10, and 15. Okay. And then I want to do my differences. Diff 1, let's call it. On that next row on the TI-Nspire, you have the option to set a formula. And so diff 1, I want it. I got to go to menu. I have to go to data. Number 7 here is list operations. and I want a difference list from the list called triangle, and I get that from the var menu. And so there's my difference list. So there's no need to lock a list because the TI-Nspire lets you define a list and give it a formula to begin with. Okay, back to our lists here. Let's imagine for a minute that you haven't figured out a way to build that algebraic model. John's going to show you a way a little bit later on. But what is wonderful is we know that it is a quadratic model. And I'm going to quickly turn on the transformation graphing app, which is a way to do sliders in the TI-84. And when you have transformation graphing activated on the color calculators, it will say so at the top. And you'll notice that the graphing indicators on Y1 and Y2 have turned into play pause buttons. Otherwise, my graph is still the same. I want to test out a quadratic model, and thankfully they are built into transformation graphing. So I'm going to arrow to the left like we did when we got the tracer ball, and I want to come down to Y1 and I want to choose a model here. And this one here is a vertex form model, and this is a factored form model of a quadratic, and I want to just use ax squared plus bx plus c, the standard form model. And when I graph that, the values for A, B, and C have started out as 1, 1, and 1. I arrow to the right to change them. So my A value, I don't think should get as big as 4. Whoops, sorry. So I have to arrow to the left to make it smaller. I want to do something between 0 and 1. This setup here, I hit my graph button and I can have my step size be a little bit smaller. Maybe I'll make it 0.1. And I go back to the graph, and my A, I might want to change my A value till I get something that looks like it might be more like the curvature. I arrow down to get to the B value, and I can change my B value, and I arrow down to the C value, and I arrow to the left because it looks like my C might be 0. But this is a way to have students use basically a slider to change the quadratic to see what this is going to look like. Now on the Nspire, when you do that, we want to, when you are graphing a scatter plot on the Nspire, you want to do the type of graph is going to be a scatter plot. There's other ways to do this, of course. I want to use my stage. I want to use my triangle for my Y value. Okay, I want to zoom fit. Oh, excuse me, zoom data, sorry, number 9. Okay, and what we can do on the TI-Nspire is we have the opportunity, of course, to graph a function. Control G gets me my graph window again, but I want to do a function graph. And I want to put in x squared. And what is the TI-Nspire allows you to actually drag this graph, and you can see how you can manipulate that. So that's another way to model with a draggable, manipulatable function. And of course, we could always go and use stat calc and do a quadratic regression. I'm not going to do that because John has more to do with the triangle numbers in his part of the session. But what I want to do before we leave is I want you to consider this last one, which is triangles of all sizes. And actually, I'm looking at the time. We don't really have time to do this, but this is in your webinar documents. And when you consider it, you want to consider triangles of all sizes, not just the little ones, but that there are big ones. So that this triangle, when we get over to the 3 stage, I have 1, 2, and 3 of them. And then I also have all the little ones. So when you get to this part, when you're working on your own, consider all the triangles that are there, and you're going to find that this one is not a linear model nor a quadratic model. This is going to be a cubic model that's going to have the third differences be constant. The last kind of growth that you can think about as a model is exponential growth. So we said linear growth has a constant additive amount or subtracted amount, a constant difference. The quadratics have the second differences are constant, and a exponential function has a constant multiplier, so it yields an exponential model. And I have so much more to show you, and John has some things too. So I'm not going to show you the exponential activity right this minute because it's something that I've shown in other webinars, but I'm just going to pull up the activity, the growth investigation, linear versus experimental. This is in your webinar documents. And actually, I do just want to show you one quick thing. I'm going to quit the transformation graphing app and going back to my y equals. I'm going to just turn off my plot. And what I want to show you just really quickly is the idea of using your table as a way to model growth. And so what I'm doing here is I am putting into the graphing screen, to our y equals, I am putting in a linear model and an exponential model. And when you are going, I'm not even going to look at the graph at the moment. I want to look at my table, and my table here, I'm going to let, instead of, I often start with just filling the table with auto and auto. But what I'm going to do here is I'm going to let my independent variable be auto and my dependent variable be ask. And in your packet, in your webinar documents, there's information on how you can get this on the TI-Nspire. There's instructions to do it here as well. And so what we want to do here is under my Y1, if I press enter and then arrow down, it's going to give me my linear model. And I ask students, how does this pattern grow? And they tell me that it grows by adding 2 each time. And this Y2, which was the exponential model, I don't tell the students that these are these models. They find them out. We define them after we've done this. But when we see how this pattern grows, this time, instead of adding the 2, we multiply by 2. And so students get a dynamic table experience here, and they can watch how the pattern grows. Now, there's so much more to do here on that, but those are just a taste of some of the different tools you can use as you're experimenting with patterns, whether it's a pattern that comes from a scenario like salary growth or population growth, or whether it's a pattern that comes from a visual pattern like the one I shared or plenty others online, or whether it's a numerical pattern. So I'm going to just take just a few minutes because I've talked for too long already, and I want to show you some ways that we can do support for support for rules that we already teach. And what I'm going to do here is I'm going to show you these. Some of them I'm going to show you statically, and some I'm going to show you dynamically. So first of all, we've got exponential growth. When we have exponent laws. And the first exponent laws that my students encounter is multiplying the same base. And what you can see here is that I actually have students go through a pattern on the home screen where they multiply numbers, and I give them an annotated list of powers of 2. You can also do this with powers of 10. Let's come here and show the powers of 10 because it might be easier for us to just look at. If I do 10 to the 3rd times 10, That gives me a 1 with 4 zeros, 10 to the third times 10 squared. That gives me 5 zeros, 10 to the third times 10 to the third, or let's just make it 10 to the fifth. Okay, whoops. What students are going to see here is that they are going to be able to build a pattern. They can count the number of zeros and they can figure out, learn for themselves that the exponent laws are true. And if students develop the pattern and name the rules themselves, that makes it learning much more durable and long lasting than if we just tell them the rules. Let's quick jump over to the Nspire. I'm going to use the scratch pad. The wonderful thing about the Nspire is that if I give students, I can do the same thing numerically. 2 to the second times 2 to the third is the same as 2 to the fifth. 2 to the second times 2 to the fourth is the same as 2 to the sixth. But the wonderful thing with the Nspire is I can also do x to the m times x to the n. This is the Nspire. Whoops, I turned off my CAS mode. The way that you turn off your CAS mode is under Dock, number 7, Settings and Status. The document status, we can have our CAS mode. Sorry. My CAS mode was off for a minute. I was doing something earlier. Okay, let me arrow up and grab my previous computation and press enter, and it's going to give me that calculation. It's also going to do, if I do the fraction rule, if I do x to the m divided by x to the n, it's going to do that for me. So you can build these rules with your students. I want to show you here. You'll notice when you do when you do calculations on the TI-Nspire, like x to the 7th divided by x to the 2nd, or x to the 6th divided by x to the 2nd, these alarm signifiers are showing you that you're going to have domain differences. Okay, there's so much more that you can do in terms of rules that we already teach. Let me quickly show you in the 84 how we can build the idea of negative exponents. I'm going to use my fraction template, which is my all-time favorite thing about the TI-84. That stacked fraction, here it exists with alpha x. And what you're going to do with this is we're going to take a look at the table. And in this time, when I set up my table, I am going to do an automatic dependent, but I'm going to ask for the independent variable. And so I'm going to start with x 2 to the 4th, I'm sorry. 2 to the 4th was 16, 2 to the 3rd is 8, 2 to the 2nd is 4, 2 to the 1st is 2. And I asked students, how are the exponents changing? On the left, they're going down by 1. How are the results changing? I'm dividing by 2 or multiplying by 1/2. If I do 2 to the 0, I get 1. And then 2 to the negative 1, I get 1/2. 2 to the negative 2, I get 1/4. And students can see how these negative exponents and 0 exponents occur because we keep dividing the result by 2 and we are subtracting 1 from every exponent. Okay, I want to just tell you a couple more things before I pass it back to John. We don't have time to go through all of these, but in your webinar documents, you're going to see that we've got logs, and you can have students building the idea of a log of a product, that the log of the product is equal to the sum of the individual logs, and I build it with log of 3,330 and then 3, and they can see how the decimal portion keeps the same. And we can figure out, well, what's really happening is it's doing log of 10 plus log of 3 or log of 100 plus log of 3. You can also do the inverse rules for logs. On the CAS, on the TI-Nspire CAS, you can build the idea of the simplifying radicals and compare it to the factors. You can also show how common confusions, you can clear up common confusions for students, that the square root does not distribute over a sum. And the last thing I'm going to show you is that you can, on the TI-84, and also I believe on the Nspire, you can do power patterns of powers of I. And then there's a really neat pattern that's going here with conjugates. If you multiply conjugates, you can have your students figure out what the numbers are here. And finally, which we don't have any time for, if you divide conjugates, there's a really fun activity with a surprising pattern that shows up that we call I's surprise, that is in your webinar documents. Okay, John, I think I've talked way too long, but take it away.
You know, I just loved everything you did. It was so great. And it ending with all that wonderful surprise stuff that it just was like gifts that keep on giving, you know. So thank you so much. I'm gonna share my screen here to put in some fun stuff here, and let's get this document. That was cute, but I don't want that. I'm going to put in this. And thank you so much. There's so just to clarify, some of the questions were about what will we get at the end, and so there's a document all on some of the I surprise and other things and stuff we didn't even talk about. So what I'd like to do is, we mentioned earlier, Karen, you did a great job looking at so many entry ramps for students to be able to do a discovery. And I'd like to kind of give you a sense of how I might use the triangular numbers that you see in front of you on this document. And it's called, and they're figurate numbers, it's called Name Gang. You'll get this activity. What is fun about this is how I use this practically in my class. And I've done this in a calculus class, and I've done it in a algebra class, and you could do it in really any level, and you can do it on any platform. So all I'm going to do can be done on an Nspire or on an 84. So I'd put this slide up and ask students to do a think, pair, share. You've seen already how the pattern works. And then just not only do I want the next 3 terms, but the 1,000th term. And what I don't want is them to say, I know the answer and I'll find it on the internet. You know, I pull them away from just the answer, but for the journey. And what I'd like to share with you is then, while they think about it, I will ask them, and this little animation also is something that is kind of cute. And I'll put this in the chat here also for you, that you can download it if you'd like, but it is a way to just describe what my students will be doing the first day of class. Is I will put a timer or ask students to volunteer to be the timer. And maybe in this scenario, I have a 13 small class, right? And they all start the timer at the beginning at 0. And then I will ask students to say something about themselves in class. And you might wonder, what does this have to do with patterns? Well, there's a surprise. And so as the timers start and they say their blurb, the person, after they say their comment, if they're holding a timer, they will actually stop their timer. And so we'll have a bunch of elapsed times per as the students keep talking until the last person with the timer has talked. And so now we can see that 3 people talk and 5 seconds have elapsed. 5 people talk 8 seconds. 8 people have elapsed, talked 16 seconds, 12 people. The time keeps climbing. And we really have what we call an accumulation function going on. And what's neat about this is I asked them to think about what would their graph of this look like. And so let's get that to minimize. And if I ask you, what do you think? First of all, they also decide to tell me which variable goes on which axis. And so after so many people, we could plot this if we wanted to. Before I asked them to plot it, though, I asked them to kind of sketch this, and they might see that the elapsed time, because they said about the same thing each time, it may not be perfect, but it's going to look really linear. And then we find the equation of this, and there is an activity in your handout that in your document that will describe exactly what I just mentioned, and it'll show you this, and it's called name dropping. And what's fun about name dropping is it's easy to do in class on the first day, and then I'd like to tell them, well, what if we did something even more exciting? And I said, not just your name, but after you're done, you have to say, I'm sorry, when it's your turn, you have to say everybody's name who went before you. And it's a really great icebreaker. But sometimes I have a 50-minute class. And so I ask students to think about, what would that data look like? And do you think we could even do it in our remaining class time period? Now, as you think about it, most of the time on a day that they're paying attention, they would likely draw something that would climb not at a constant rate. And if we look at that pattern, we'd see there is a very high time elapsed for that last person who has to say all the names compared to the first people. And what I want you to notice is, and my students notice, and I mentioned the deltas in the chat as Karen showed the deltas, the change in the consecutive numbers, which is a first place, that they might see that consecutive numbers going on. And here's the cutest thing about this, that it is, well, most of my students guess exponential, but if each were required to only say their name and maybe an adjective, it might be only like 1 second of time. I'm going to use 1 for simplicity. And the next person would have to take more than 1 second has elapsed, and they'd have 2 names. And so we can simulate that very nicely with, you just said one person said their name. I will include that, but I have to say 2. Now I have to say, I'm going to just climb there and do it this way. Second answer, I have to say 3 names. And then the next person has, you can smell it, can't you? These triangular numbers are showing up. And I don't know about you, but that's to me a very big surprise. And you kind of can get that sense of those, each of these, the person who had 5 names will feel that this is kind of a longer time for them, and these deltas are linear. Notice how 1, 2, 3, 4, 5 are the deltas, and that's the deltas are consecutive, and that's why these triangular numbers are connected. So also the connection to the fundamental theorem of calculus is kind of fun, how that also ties in with differences. So that's the name game. And when I have this, I actually see how students are kind of connected to it. I will share, and just because it's kind of been alluded to, and we have a lot of ways we can get to building that formula without necessarily, well, there's many ways. One of the suggestions I will ask is, what if we doubled the numbers, each of these? Can you see a pattern in there? And many of the times what students will do is that the consecutive gaps are doubled also. And this is fun to notice that there's a lot of richness in this pattern, and you might even notice these are called the rectangular or the oblong numbers. And we can see that many times this pattern is easier for students. Let's get to that area that they can go, and I apologize for the long scrolling. Here's a cute way to do it with the dynamic table, but we would see products. And then having the rectangular numbers gives us the oblong numbers. So this can be a neat way to get that quadratic formula by changing the question. Okay, so there's another cute thing I want to share with you that is a delightful thing that is involving some stacked fractions. And I've used this again with any platform and with many, many different grade levels. And the first one is so rich because the patterns just never stop. So let's show the first one. We stick one in, and we're just really playing with the home screen. And then what we like to do is build a sequence on the home screen. So what I'm going to do is type 1 plus, and there's many ways to get the stacked fraction, but the cutest way, whether or not you have a Python or an 84 CE, is alpha and then press the X button. And we're going to put the second answer in the numerator. And I can use the right arrow or the down arrow to put in what I like is a 2 here.
And John, that stacked fraction icon is now above the X button on newer versions of the calculator and emulator.
Another cute surprise is that it's still there even when it's not on there, that icon. And so that icon doesn't show on your 84 CE. If it's the latest OS, you can still get this. Or you can do the old-fashioned way. It's always here too, N over D. And then it's also, what I did was I pressed alpha y equal to get to that shortcut menu. And it's also in the math menu under num. So, there she is. So and it's in the catalog. So many places. But you notice 1 3/2. And if I just hit enter, what I did was I took 3/2 and shoved it into answer. And now I have 1 plus 3/2 over 2. And do you see what we're building now is what's the next denominator? Well, you can type it in the chat. And then do you notice anything about the numerators compared to the denominator? And sometimes students, very nice, good job, Mary. And so we might notice how are the denominators changing. And so the next one might be similar to the numerator. And so if you're guessing that it might be that numerator less than, sometimes students think, okay, the next numerator is 1 less, next denominator is 1 less than the next numerator. You can see if I go too fast, I might actually get my tongue all twisted on all these wonderful patterns. Or looking at the numerators and the denominators, we have a cute way to go. Now the handout will explore all of these, but there's an added richness that if I keep pressing enter, I may not just I lose the fractions, but I also converge and get the distances between these two answers are smaller and smaller until what I put in is what I get out. And that is another pattern too. And so just to kind of show that with a PowerPoint here, and let's find that. I have a lot on my screen here. There we go. And this is, there it is, example 2. Okay, so thank you. Here it is. What I had was this was the entry and this is the answer. And if I keep pressing enter, what will happen is sooner or later these answer and enter, the answer, what I put in is what I get out. And so now I have a simple equation to solve and I only have one solution. The other way this can be modeled is what you're getting is you're feeding in. Remember 3/2 was our first one? Well, now I put 3/2 into the next answer. And so I'm going to get a lovely continued fraction here that shows this. And what it's cute is that it actually keeps going forever and it shows to 2. So it brings a lovely pattern of what are you doing. And my favorite part about this is that you have the cute thing here is the patterns never are up to your time and imagination. So you can change that 2 to a 3 or a 4 or a B, and you'll ask the same questions and you'll get different patterns, and that's in the answers in the handout. But there's more, and this is what I want to end with. What if we flipped it, and now I put in the answer in the denominator, and here we'll go right here. Quadratic fun. So now I have 1 plus 1 over answer, and look at this. 3 over 2, 5 over 3, 8 over 5. Do you smell the denominator, what that smells like? What are those numbers? Yes. And I don't know, it smells like Italian to me. And you can see connections between the numerator's sequence and then the denominator's sequence and how they sum together. Lots of fun stuff. But notice we've got a little quadratic equation going on. And you and I know, if you've been around a little bit, that what it would go to. But last I'd like to share with you is this cute kind of thing that to me is just delightful fun. So when I'd, been in primary school, I might have been told, to show how to use 1 2/3 as taking the 3 times the 1 and adding it to the 2, right? So we could do the same thing. So here's my quadratic pattern. and if I do recreate this and say answer times fib, or answer times b, Freudian slip, but plus c, well, what we're going to get is if I stick an n over d in, and just now I do a little bit of, I'll just close it with this, a little bit of fun arithmetic here and simplify. If n over d was my answer, my next pattern fraction will be the numerator of the previous fraction, and the denominator will be the sum. And if b and c are 1, you can see n plus d. So this is really rich. I'm going to have to stop because we can't go till 10 p.m. tonight. I know we'd love to, but there's more in the handouts for you to play. But there's cute stuff. We got a little bit of a teaser there. And so I'm going to stop sharing. We have a drawing, which is the best part. And that's another surprise.
Thanks so much, John. Before we do the drawing, I know, Karen, you want to mention how how to reach out to the TI teacher community on Facebook really quick?
Yeah, absolutely. If you're out on social media, come find TI Calculators wherever you are, at TI Calculators, hashtag T3Learns. But on Facebook, there's a TI teacher community, and we really hope you'll join the conversation. Mike, can I just have 10 seconds to show you that if you are looking for more PD this summer, the TI website, if you go to Educators, Professional Development, and you go down for teachers and teams, okay? We've got T-Cube summer workshops, both in person and virtual, and T-Cube regional summits coming to a city near you, which are shorter one-day type events. And thanks so much, Mike. Just wanted people to know where they can find more summer learning.
Thanks, Karen. And now on to that giveaway. Donna Smith, congratulations. You're receiving a TI graphing calculator of your choice. So Donna, hang tight. We'll be reaching out to you over email in the coming days here to get some information, but start thinking about which calculator you want. To receive a certificate of attendance as well as a link for the documents for tonight, go ahead and click the link in the chat window. And if that link isn't working for any reason, just hang tight. You'll automatically get a follow-up email. And in that follow-up email will be links to everything, the certificate, the documents, the recording. You can watch this all at your own pace. So huge thanks to John and Karen for everything they shared tonight. Thanks to everyone who joined us for sticking around and registering and attending. We really appreciate you giving up your time as well. So huge thanks to everyone, and we hope to see you back online next week. Have a great night.